hear me. And so this is the second talk of this CHEETAH webinar, and I'm Giuseppe Nenna from ENEA, and in particular from a Portici Research Center. And today I will speak about something about printed polymeric microlenses for solar microconcentrators. This work was realized thanks also to the Helmholtz Zentrum Berlin and to the Martina Smith laboratories. So here we are. This is the outline of my presentation. We will speak about solar microconcentrators a little bit to see what usually they use it also in literatures, and then we will go to see some kind of characterizations for this kind of optical elements, how to design this kind of systems, and how we can realize these systems also with polymers with very high viscosity. And at the end we will see also something that we must do before realize the solar concentrators with this kind of optical elements. Okay. Here we can see, as all of you know, we can see which are the elements that we can, the optical elements that we can apply for this kind of microconcentrators. Okay, we can have refractor elements, some hybrid systems, also to split the light and focus in different points and with different wavelengths the light spot. And recently a lot of people are working on luminescent concentrators, also with use of quantum dot composites, and in particular here I showed something that are quite recent and was showed in Nature Photonics in 2014. Here instead we can see why we use solar microconcentrators. In particular, why we are trying to scale down the area. We know, in particular, all of you know that it's very important the area for the solar cell and the active area. And this is with the log scale on the area axis. And so we can see how the efficiency drop down very fast, changing the size of the solar cell. We know that also with one imperfection during the development of the solar cell and building layer by layer the stacked devices is very easy to find some problem in a very big area. Instead, we can select our solar cells, low dimension solar cells. And so we can reach very high efficiency with the reduced area. Here there is another example on with the system that we can use for this kind of solar concentrations. In particular, here we can see an hybrid system with a refractive system and also reflective and in particular a scattering system, no? Because there are some prisms coupling elements to guide the light on the border of our substrate, and on which we can apply the PV system. So here is possible also that on the waveguide border we can have a very good output without no so much difference on all the border of the substrate. Here there is another image of this kind of possibility, and we can see that it's very important to have an understanding about the geometry of our system, and in particular about the length of waveguide and also the thickness of the waveguide. In particular, the thickness is very important, and also and the optical efficiency will drop down very soon if we don't care about to this kind of parameters. Here instead is the system that today we will try to describe in such a way, and with only one refractive element that is made by a microlens array, microlens system array, and this kind of systems can be useful on very reduced size in solar cells, and we will see how is important also the optical shape and the geometries, the constraint that we must apply to our microlenses to be useful for this kind of application. Usually, to characterize this kind of optical elements, we use some interferometric systems like Twyman Green or Mach-Zehnder system. In particular, the Twyman Green system usually is used more for reflective elements, not so much for microlenses, and also because when we use this kind of a system, we have to pass through time in between some optical elements that we use for this interferometric system. In particular, there could be a double pass in a microscope objective that we can use in this kind of applications, and so there are some problems also in the reconstruction of the interferometric fringes, and there should be some systematic aberration that also, in the worst case, can affect a lot the interferogram, and we cannot resolve in a good way the shape of our microlens system. So usually we use a single pass interferometer, and so something that is more close to the Mach-Zehnder system, and in fact also see the slightly tilted interferogram that we can see of the microlenses, characterized microlenses. We can see that is much better the interferogram related to the Mach-Zehnder interferometer. Using but the Twyman Green position is important to also for Mach-Zehnder interferometer to have an understanding about the radius of curvature of our optical elements, while in confocal position of Mach-Zehnder interferometer we can have an understanding about the focal length of our system. Here we can see that also applying a single only one of the two paths for the interferometers, we can have an understanding about the structural imperfection in the far-field image of our structure. In particular, here it's possible to see the differences in between an optical microscope image and the confocal plane in the far field of our microlens, and we can see that using only an optical microscope is not possible to have an understanding about this particular structural imperfection that could affect the guidance of our microlens. So here instead it's possible to see how change the interferogram of the microlens if we tilt a little bit the microlens respect to the microscope objective, and so we to have an increase in the fringes of the interferogram, and to analyze better the shape of our microlens. In fact, if we tilted more our microlens, we will have the appearance of more fringes, and so we can better reconstruct the shape and have an understanding about the conic shape of our microlens. Here is possible to see what we can do with the interferogram, and so the number of fringes, the distance between the fringes, and so on, and so which formulation can help us to have an understanding about the shape of our microlens. In particular, we can see that the Zernike formulation can help us, and in particular we can use the coefficient of this kind of formulation to have an understanding about some aberrations about our geometrical structure, about astigmatism, coma, spherical aberration, and so on. And in particular we can have a figure, a plot describing how our surface is different from the surface related to a conical shape that we would like to use to compare our shape. In particular, here it's possible to see what is the error in between these two surfaces, the perfect one and the one that we realized, and to quantify the optical degree of our microlens. Here instead I would like to show something about some processes that we can use for this for realization of this kind of structures. In particular, the first process that I'm showing now is related to the hot embossing process. Is a very simple process that we can apply especially on polymeric substrates. But respect to the ones that I will show soon later, is in this case we have some constraint about the geometries. So if we would like to change the geometries, we have to change the shim, and so is a cost-effective this kind of solutions, and so we have to care about the polymers that we can use for this kind of process, but also about the geometries. Every time we would like to change the geometries, we have to change everything, These are some microlenses that we realized also on top of OLED systems, but it can be applied for every kind of staggered optoelectronic devices. Here, instead, we start to speak about the inkjet printing solution. This is another kind of solution processes that we can use to realize this kind of structures with a freedom, with much freedom respect to the geometries that we would like to realize. We can change the shape of the microlenses and also the sides and the steps in between the microlenses and we can also use only the polymer that we think to realize our structure, because it's an additive process. So it's important also for to spend not so much materials in the fabrication processes. So, but in this case, we have to care about especially the hydrophobicity of our substrate. In fact, usually on the substrate we have to apply some an extra film, highly hydrophobic extra film that is very thin in this case, and so we to increase the energy of the substrate, and so to give the possibility to realize a higher shape of our structure. Here is possible to see how the Theos PF-Theos layer will affect a lot the drop that we will use for the realization of our structure, and how so the energy surface energy will change the shape of our structure. In particular, it's possible also to see that transmittance of this film is very good, and so it can be applied in an easy way for this kind of processes. Here instead are reported some solvents and solvent mixtures that we can use for the preparation of this kind of printed matrix, microlenses printed matrix. In particular, it's possible to see that we can use very different solvents, not only about with very different boiling temperatures, but also with different surface tensions. That is another parameter that is very important in this kind of application. And the mixture of these solvents can also affect these two parameters. So we have a lot of possibility to explore to realize a good shape for our elements. But it's very difficult to have a very good optical elements. In fact, if we can, from this picture, it's very difficult to have an understanding about the good geometries that we can use for this kind of application. It could be considered a disaster, no? Because if we see only these pictures, we can say, okay, we made a lot of mixtures, solvents ratios, but we have no possibilities to realize good optical geometries. Instead, we can see here that using only an NMP solvent or mixtures with the toluene solvent, we can have also the possibility to have a good shape, and for the PMMA based ink in this case, and so a very good geometry for our system. In particular, it's possible to see that there is a very big change also in the geometry, changing the solution and the mixture in these two cases, and it's very it's simple to see how the error respect to the conic shape that we are seeing in this moment for the NMP solvent is very low, and so we can realize a very good microlenses also with one kind of solvent if we are able to choose the solvent, because we had to realize all the possible experiments that we already showed to have an understanding about the boiling temperature and so on. So is not so simple in the beginning, but after when if we are able to adjust our parameters from this point, we can realize very good matrix with this kind of optical elements. In fact, here is possible to see how also the matrix the matrix will change, and also the shape of microlenses changing the step size in between two microlenses. In particular, it's possible to see on the right that the roughness of the microlenses increase, changing the step size, and this is much true if we use more than one drops on for each microlenses. In fact, on the right we can see that the roughness is going in a bad way, and so we have to reduce the size of the step to have also the appropriate evaporation of the solvents. So we are free in geometries, but not so much. But if we apply some solutions like the possibility to have an homogeneity in the evaporation of the system, we can use also different step size. So we have to care about these problems. Changing another time the number of drops, we can see that the roughness is going in a bad way also for the reduced step size. So we have to pay attention on this also. In particular, changing the drops, we see that is very difficult to have a good far field and in the confocal position. In particular, we can see that the roughness is very high also in with one drop, and so the interferogram is very difficult to be characterized. In fact, in the pictures on the right, we have to see the good interferograms, but are very poor at the moment. So the importance in this is also to have an understanding about the processes. I mean, for example, temperature. We can hit another time the polymer to cure the polymer and reduce the roughness of the system. In particular, changing the curing temperature, we will have also a change, a completely change also in the geometry of the system and the conic constant. In particular, the conic constant is the one that we used to have an understanding about the errors on the realization processes, as I showed before, and so is very critical, this aspect. Changing the temperature, we see on the right the picture in which it's possible to see how change dramatically the geometry, but also the roughness of this system. In particular, it's possible to see at 100 degrees we don't have so much differences in roughness, and in the picture A, it's possible to see that it's very difficult to have an understanding about the interferogram. And we have an ellipsoidal shape of our microlens with a conic parameter that is around 0.7. Heating more our structure, is possible to see that we have a more hyperbolic shape, and is with a very different arrangement of the polymer, and but it starts to appear in a very good way the interferogram fringes. We have only some problems on the border of our microlenses. Instead, applying an higher temperature, we cure also the border, and we realized a good optical shape elements with a shape that is in between spherical and ellipsoidal one. So we have to pay attention also to this process, so to realize, to select in such a way, in a good way, the solvent mixture and the temperature at which we would like to treat our optical elements. Here it's possible also to see how easily now we can reconstruct the focal length, because if we have an understanding about the radius of curvature related to the conical shape, we ended the height and the radius of the base radius of our optical elements, we can have an understanding about the focal length, and we can see if the number that we calculated in this case is the one that we measured because of the interferometric system. So it's possible to see how the focal length, the radius of curvature, and how is different also the calculated focal length respect to the one that we measured for these two last optical elements. And we can see that the calculated one is very close to the one that we measured in the beginning using simply our interferometric system. Another way to have the realization of microlenses because of the solvent mixture with the polymeric materials is the one that I'm going to show now, that is the pyro-electrodynamic dispensing method that we realized also in collaboration with the CNR and the group, the Pietro Ferraro groups, and in which we have a reservoir on the glass, and because of the thermal stimulus on lithium niobate substrate, it's possible to collect the part of the reservoir on the other substrate and realize microlenses without nozzle that we have to use for inkjet printing method, the inkjet printing method that I showed before. This is a very important method because in this way we can realize optical elements simply using without the nozzle, as I said already, and with very high viscosity, materials with very high viscosity like Silgard, the PDMS. So is very crucial for this kind of realizations. Also because in this case we can also use more material, and so we can realize a bigger elements, optical elements, that are very important for our study, because with inkjet printing we can realize something like 100 microns of structures in the base, but we would like to concentrate light on cells that have the same size, so we cannot apply simply inkjet printing processes. So we have to pay attention also to this kind of dispensing methods. Here is possible to see how we realize the microlenses with this kind of structure. There is a formation of a liquid bridge, and after the realization of the microlens. Because of a change in the charge of over the substrate, that change the charge also on the reservoir. So there is the possibility to have the formation of this liquid bridge, and so the formation of finally of our microlens. In particular, we can realize the microlens, as I said before, with polymethylacrylate, but also with the Silgar material. Here is possible also to see the characterization of PDMS microlenses and the shape of these microlenses, and how change the focal length, changing the diameter of the microlens. In particular, we can pass between 260 micrometer of diameter, going also over the double of this, and going from a focal length around 700, 800 micron to also more than 1 millimeter. Here is possible also to see that changing the time in between a realization of an optical element in between another, it's possible also to realize some lines and so some cylindric lenses that could be useful in this kind of applications. Here I would like to show only some constraints that the group of Martina Smith gave me at the beginning. In particular, these slides were made by Diego, And in such a way they showed very well which are the constraints. We would like to have a very big difference in the area between the active area of solar cells and over the optical elements, and also the radiation distribution would be crucial. In fact, we have to pay attention on this because also, as Maria said before, is we have to cool a lot the solar cells, and is difficult to remove the heat, and we have to care also on the distribution of the light on the solar cell. So we have to care to a lot of elements, and for example, like Diego said in the beginning, we can also use optical index matches, and we have to care about the angles with which we used to use the solar cell. So there are some simulations that we have to realize to have an understanding about the degree that we can use also for the light, the incident light. Among the printing techniques, we have to pay attention about not only the way in which we can remove the roughness, and how we can which one is the solution that we have to use, but also the profile of the radiation, and also the incident angles that we have to use in the track systems. That if we would like to use this kind of concentrators, we have to think another time, like for the bigger modules, to the track system too. So here there are some simulations in which I can show that changing a bit the degree, also with 5 degrees, the light spot will change its position completely, and with 10 degrees we have only few rays that impact on the objective that on the object that we realize for this kind of simulation. The object that I used in this kind of simulation is almost double in the size respect to the micro solar cells that we saw also in the Maria presentation. So we can see also with a very few degree we lose all the rays of the spot, and so we have to care to pay attention also on this task. Here instead, I would like to show some initial work on the possibility to put nanoparticles inside microlenses to realize diffuser elements. Here another time we realized the same experiment, changing the percentage of in this case TO2 titanium dioxide nanoparticles, and we can see that with 5% of the amount we have a very rough structures. In this case we can try to realize something that I already showed in the beginning of this talk, in which we used some refractive systems like microlenses, and also diffuser systems like prisms, but also we can use this kind of elements on the other side of the substrate to realize the possibility to guide inside the light inside the substrate. So here also is possible to see how change the anisotropy of the light, the scattered light, and how change the far field because of the scattering of microlenses. It's possible to see that the pattern of microlenses will be repeated a lot of times all around, and the angles of the reflected light can be very, very big, and so we have a lot of percentage of the light that can be coupled inside a substrate. So in this talk we spoke about something about solar microconcentrators and the possibilities to use different optical elements to realize them. How we saw something about the characterization and also the realization of these polymeric microlenses, how to evaluate the system, and in particular the shape of the microlens, and how we can realize microlenses also with high viscosity system. And at the end, how to, not so much to test, but to simulate the solar microconcentrators for our purpose, to give them the possibility to be useful in the real microconcentrators. Yes, there are a lot of things to be done, a better understanding about the realization process. Sure, we can better optimize this, changing better the solvents and the percentage of polymeric materials, and we have to better simulate all the system, and then evaluate the microlenses that we would like to apply, also to have a better distribution of the light on the solar cells. And so I would like to thank you very much, and also all the people that helped me, not only from ENEA but also from Helmholtz Berlin Centrum, and from the CNR laboratories of Pietro Ferraro. Okay, thanks a lot.